Hello, and welcome to the Software Carpentry series on Matlab programming. This is the first episode in the series, and we will briefly tour the world of Matlab. We start by making a few observations on what scientific software should be like. Probably the most important aspect of good software is that it is written for humans rather than machines. Humans are the ones who have to understand, critique, and debug software, and your task as a programmer is to make it easier on your fellow programmers. Software written for humans is, first of all, written in a readable format. The structure and purpose of code should be obvious. Software written for human emphasizes what is important. Usually, we write code to solve particular problems in particular domains. Good code should emphasize those domains rather than the low-level algorithms that are utilized. Good code should always be testable, which means that its purpose must be clear enough that tests can be written. Finally, good code should be efficient. We will see how Matlab provides efficiency without sacrificing readability and testability. Contrast good code with bad code. Bad code is hard for humans to read. It emphasizes small efficiency gains over human readability and testability. Often, it re-implements functions that have already been written and tested by someone else. Also, it can be hard to find the domain-specific algorithm among all of the low-level secondary routines. Matlab is a tool to help scientists write good, efficient programs and write them quickly. It provides a wide array of efficient mathematical routines that have been tested by someone else. Also, it provides a high-level programming language that helps programmers express their work as mathematical ideas rather than programming details. On most systems, Matlab opens a graphical environment like this one. It includes a list of all variables that have been created. The center of the window is a command line where we can create and manipulate variables. Most programs are written in the editor, which provides a way to create functions that can be called from other functions or from the Matlab command line. We will cover programs in 2 lectures on flow control. The Matlab programming language is built around the multi-dimensional floating point array. We will cover floating point arrays in the lectures on programming basics, array indexing, and linear algebra. Typical flow control structures like for loops, while loops, and if statements are available and are introduced in the lectures on flow control. Throughout this lecture series, we will return to the idea of data parallel programming. In data parallel programs, the programmer is encouraged to think at a high level of abstraction. Implementing algorithms, which typically takes a lot of loops and indices, is handled by the programming language. This means that code is easier to write and debug, and typically, data parallel programs are much faster. This simple example demonstrates the difference between a typical program that emphasizes loops and a data parallel implementation of the same thing. The data parallel approach places more emphasis on the objective of the operation than on the implementation of the objective. We will see numerous examples of how data parallel thinking can simplify and speed up your code. So why learn Matlab? Over the last 20 years, Matlab has become one of the most common languages in the scientific programming community. Its wide range of built-in functions allows rapid prototyping, and it scales well to large production platforms. Perhaps its biggest strength is the support community, which has provided algorithms based on recent publications across many fields. In our next episode, we will start to examine the basic data type in Matlab, which is a multi-dimensional array of double precision numbers. Hello, and welcome to another episode of the Software Carpentry lecture on Matlab programming. In this episode, we'll have a look at how to do linear algebra. The basic data type in Matlab is the multi-dimensional array of floating point numbers, and these arrays should be treated like matrices from linear algebra. In higher dimensions, we can think of them as tensors. For instance, if we multiply the arrays A and B, the product is found by the rules of matrix multiplication. Aside from traditional operators, there are also a lot of functions that operate directly on matrices. For instance, sum can be used to add up all of the entries along one dimension of a matrix. In the first example, we are summing over each column of the matrix, which happens to be the default. In the second case, we sum over each row. Dimensions in a matrix are numbered 1 through n, and they are in the same order as the indices you use to access a single element. Here's a long example of what we can do with array operations. Suppose we have been observing the progress of a disease in some test subjects. Each row of our array corresponds to one patient, and each column is an hourly count of responsive T cells. This means that the first column of our data is the initial T cell count for all patients, while the first row is all hourly samples for patient 0. The mean of the data along axis 1 gives us the average across all patients for each hour. This gives us the normal progress of the disease. The mean along axis 2 gives us the average T cell count per patient across all times, which can be useful if we want to normalize our data. It might be even more interesting to look at what happened to people who started with no responsive T cell count at all. The first step is to select the first column of data, i.e. the initial T cell counts for each patient. If we compare these to 0, we get a Boolean array with true for each row of the array that meets our criteria. If we use this to index the original array, we get the 2 rows for which the count at time 0 is 0. Now let's find the mean T cell count over time for those people. Once again, we start by selecting column 1 and testing it to create a Boolean mask. Using that mask as a subscript gives us the rows that have 0 in the first place. We can now use the mean function along axis 1, i.e. across all patients, which gives us the average behavior of patients who started with no responsive T cells at all. This example highlights the key to good matrix programming. Write high-level statements without loops and let the computer worry about how to do the operations element by element. This is just as true for Matlab or R as it is for Python. Finally, always remember that you're not the first person to program with matrices. Always take a look at the online documentation from Matlab before writing any functions of your own. The library includes routines to conjugate, convolve, and correlate matrices, to extract diagonals, calculate FFTs, gradients, histograms, and least squares. It can find roots, solve sets of linear equations, and do singular value decomposition. These functions are all faster than anything you could easily write, and what's more, someone else has tested and debugged them. All the functions in Matlab have detailed help information, accessible by typing help then the function name. You can also open the graphical help window from the menu on the graphical interface. In many cases, the documentation includes a brief introduction to the mathematical theory represented by a function, as well as a description of various sub-algorithms that might be used to handle special cases. There are other resources to help you find MATLAB functions. One of the helpful features in MATLAB is the MATLAB Central File Exchange, which includes thousands of functions for almost any type of calculation you could think of. Many of the functions in MATLAB Central are based on published research. Of course, like any software you use, you should be sure to investigate whether the functions have been tested. If you can't find a function to perform the calculation you need in MATLAB or on File Exchange, the next lecture will teach you how to write your own. Thanks for listening. Hello, and welcome to the Software Carpentry episode on MATLAB programming. In this episode, we will cover the array data type, which is the primary data type in MATLAB. MATLAB was originally designed to provide an easy way to manipulate matrices. If you've ever tried to use an array of arrays to store a matrix, you know how many loops are required to write even simple programs. MATLAB performs these loops for you, so you can write x times a times x transpose rather than writing matrix vector multiplication functions. The main data structure in MATLAB is an array of double precision floating point numbers. Arrays can have one or more dimensions, and they can be manipulated and combined in many ways that we will cover in subsequent lectures. Many applications utilize two-dimensional arrays as matrices, so you'll hear us use the terms array and matrix interchangeably. However, if we say matrix, we always mean an array with 2 dimensions. Arrays can be created from the MATLAB prompt. When you assign an array, the entire set of numbers is enclosed in brackets. Elements in the same row are separated by spaces or commas, and a semicolon denotes a row boundary. Just like in linear algebra, a row array is different from a column array. Sometimes it is helpful to create a block array by using other arrays rather than scalars in the definition. This is fine as long as the sizes of the arrays match up. In this case, we tried to combine a 2x4 matrix with a scalar, which is the same as a 1x1 matrix. MATLAB will not allow this. There are many other ways to make matrices. The functions zeros and ones will create matrices that have all zeros or have all ones. Another special function is I, which creates an identity matrix. Finally, rand creates a matrix of random doubles between 0 and 1. In a later episode, we will talk about how to program your own functions. But for now, let's explore some of the built-in functions to examine the shape and type of an array. The simplest functions are arithmetic operators, which operate on arrays in the way you would expect for matrices and vectors. Addition is element-wise and assumes that the two arrays have the same size. Multiplication is matrix multiplication and assumes that the inner dimensions agree. As an exercise, see if you can figure out what happens when you multiply two three-dimensional arrays. As a hint, try to see what sizes must match between the arrays. Other important operators are the transpose operator, which is a single quote, and two kinds of division. The first division is a forward slash, and it is equivalent to A divided by B if A and B are scalars. If they are arrays, it is equivalent to A times the inverse of B. As a convenience, MATLAB provides a backslash division, which is the inverse of forward slash. Rather than loop through each element of two arrays to combine them element-wise, most operators can be made to perform element-wise operations by putting a period before the operator. For instance, A dot times B returns the element-wise product of A and B. Do you see how this might help the programmer avoid writing a loop? Arrays can also be reshaped using two methods. The first is the function reshape. The first parameter to reshape is the array you want to reshape, while the second is a vector of dimension sizes. In this case, we want to transform A into a vector with 4 rows and 1 column. Since vectorizing an array is such a popular operation, there is an equivalent shortcut called the colon operator. If B is a 3 by 4 by 5 array, then it has 60 elements. We want to transform it to a 2 by 3 by something array, and it isn't too hard to see that the third dimension must be of size 10. What if we don't want to compute the extra dimension every time? It turns out MATLAB can compute a single missing dimension in reshape. In this case, we pass each dimension size as a separate parameter. This is fine for reshape. For the last size, we put in a pair of empty brackets, which is assigned to MATLAB to figure out what that dimension is for us. The reshape function will not add or delete elements from an array. So if the first two dimension sizes make it impossible to define an array, MATLAB is going to complain. Another important consideration is the order that reshape lists elements. In order to answer this question, we need to explore a little bit about how the computer stores a matrix. When we see a matrix, we think about a two-dimensional set of memory locations that each hold a number. The problem is that computer memory is one-dimensional. In fact, it is one long array. To think about two-dimensional matrices, we need to decide on a convention on how to store the matrix in memory. One possibility is row major order, which concatenates the rows. This is the convention used in the C programming language and in Python, since Python is written in C. In contrast, column major order concatenates the columns. The Fortran language uses column major ordering, and since MATLAB uses many matrix manipulation programs from Fortran, MATLAB uses the column major ordering. As an exercise, see if you can guess how the two types of languages store three-dimensional or higher-dimensional data. It turns out that reshape always fills the new shape by pulling elements in the order in which they are stored in memory. Since in MATLAB this is column major order, reshape fills the new array by pulling elements from column 1 and then column 2 and so on. Arrays can also be dynamically resized. If an element is assigned beyond the bounds of the current array, the array is filled with zeros for all spots that need to be created. Keep this in mind if you assign a 0 to, say, the millionth column of an array. MATLAB is going to create 1 million columns of zeros in order to have space for the new element. Remember that an array is stored in column major order. If an array is resized in a way that changes the size of the columns, then the ordering is destroyed. a whole new block of memory gets allocated to hold the array, then the existing values are copied to the new memory location. If we continuously add elements to the end of an array, like on the last slide, the overhead can be very expensive. That is why it is better to initialize an array to the size you know you will need, then go back and fill the array one slot at a time. To review, in MATLAB, the primary data type is the multidimensional array of double precision floating point numbers. All of the arithmetic operators operate directly on arrays, and MATLAB provides hundreds of functions that also operate on arrays. Among those functions are reshape and implicit resizing. We'll see many more operators in the coming episodes, including a rich library of visualization functions. In the next episode, we'll have a look at how we can select values from arrays using indexes. Hello, and welcome to another episode of the Software Carpentry lecture on MATLAB. In this episode, we'll have a look at some of the ways you can index arrays. As we'll see, clever indexing allows you to avoid writing loops, which both reduces the size of your code and makes your code more efficient. Individual elements in an array can be accessed using a comma-separated list of integer indices. In most programming languages, the first element of an array is element 0. In MATLAB, indexes start at 1. Arrays can be sliced by using another array as an index. In this example, we use the array 1, 2, 3, which we can create using the shorthand 1:3 notation. MATLAB programs should always use slices and other indexing operations rather than write loops over arrays. There are several advantages, including shorter code that is more easily understood and improved runtime. It is also possible to assign to slices. For example, we can assign 0 to columns 2 and 3 in row 2 of block in a single statement. An array slice makes a copy of the underlying array, which means that the data values are copied to a new location and subsequent updates do not change the original matrix. Slicing on both sides of a statement gives us a way to shift data along the axes. If vector is a one-dimensional array, as shown here, then vector 1, 3 selects slots 1, 2, and 3, while vector 2, 4 selects the values in slots 2, 3, and 4. Doing the assignment overwrites the lower 3 values, but it leaves the uppermost untouched. MATLAB has a function circshift, which shifts values in an array in a circular pattern. Rather than discarding the leftmost item, it is placed in the rightmost spot, and all other values are shifted left. To perform more sophisticated indexing operations, we can use an array as a set of subscripts. For example, here's our 4-element vector again, and a list with 3 legal subscripts 4, 2, and 3. The expression vector subscript gives a new array whose elements are selected from vector as you'd expect. Arrays can also be used in comparisons. When we use the result of a comparison in an index, we only get those values that satisfy the condition. Almost all arrays in MATLAB are of type double, which means they are floating point numbers. When a matrix is used in a comparison, the result is not a double. It is a matrix of integer zeros and ones. The difference is apparent in this example. Here the array M is the result of a comparison, and we can see that a 1 means that the corresponding element of V was less than 4. The array M2 is hand-constructed with the same pattern as M, but the values are doubles since this is the default. Try to use M and M2 as an index. The result of the comparison, M, can be used, but M2 fails because the indices must be integers, not doubles. Another term for an index from a comparison is a mask, because the Boolean array masks all the elements of a vector that fail the condition. We can use Boolean masking on the left side of assignment as well, though we have to be careful about its meaning. If we use a mask directly, elements are taken in order from the source on the right and assigned to elements corresponding to true values in the mask. Using a mask on both sides of an assignment has a different effect. Corresponding elements of the array fill are assigned to A if the location meets the criteria in the mask. In both cases, only locations corresponding to true values in the mask are affected. It's what happens at the source that changes. Sometimes we want to replace values in a matrix with zeros without changing the size of the result. We can use the Boolean mask in element-wise multiplication to replace locations that are less than 1 with zeros. There are two sets of logical operators in Matlab. A single AND or vertical bar corresponds to element-wise AND and OR on an array. Double AND and double OR operate on scalars only. It is usually preferable to use the single AND or single OR since they work in both cases. In logical expressions, 0 is the only number that is false. Be careful though. Very small numbers are still non-zero even if they look like 0 when you print them. To review, arrays can be sliced with vectors of indices or masked with conditionals. No matter what you do, if you are writing a loop over array elements, you have probably missed something or you're doing something wrong. In our next episode, we'll use the tools we have looked at so far to explore some linear algebra. Hello, and welcome to another episode of the Software Carpentry lecture on MATLAB programming. MATLAB contains all of the major flow control statements that you would expect of a modern programming language. In this episode, we will look at if, else statements, as well as loops. Another episode will investigate functions. We also want to emphasize that under a data parallel approach to programming, loops and if-else statements are not the solution to every problem. For instance, if we want to perform one of two functions on each element of a matrix, we could write a for loop with an if-else inside. In MATLAB, it is better to express the concept all at once by passing an array of values that satisfy each condition to A or B. To introduce loops, we will use a running example from statistics. Suppose we are given a matrix of disease statistics. Each row is a patient and we have their T-cell counts at each hour. Unfortunately, the T-cell count is missing for some time points. Those points are marked with a 0, and we need to decide what to do with the missing data. One of the simplest ways to interpolate missing data is to replace it with the average of the two closest data points. Other, more sophisticated interpolation algorithms might make use of more nearby points or use something besides a linear interpolation. We will write a function interpolate. Functions in MATLAB are stored in files with a .m extension. The easiest way to write functions is to use MATLAB's built-in editor. Type edit interpolate.m in the MATLAB command prompt. This opens an editor where we can write our interpolation function. The first line of a function file is a header, which looks like this. The header's job is to list the name of the function, the parameters, and the return values of the function. For the rest of this lecture, we will be working in this editor. A naive implementation of interpolation will loop through each person and data value. We will test whether the value is 0, and if it is, we replace it with a local interpolation. This approach is not a data parallel way of thinking about problems involving matrices. It requires that we loop through every value of the matrix. Still, it is informative to write the naive version to make sure we understand what the program is doing. In MATLAB, a for loop has the notation for index equals array. In this case, the index is I, and the array is the vector 1, 2, 3, 4, 5, which has the shorthand 1:5 notation. The statements that are repeated each iteration through a for loop are called the body of the loop, and the end of the body is marked with the keyword end. The shorthand A:B returns A plus 1, A plus 2 up to B. Another way to say the same thing is that the mesh size is 1. To change the mesh size, we can pass A:C:B. Now C is the mesh size. You might want to guess what this loop will display if you type it on the MATLAB prompt. Since a command without a semicolon prints its response to the console, in this case, we just list the numbers 1 through 5. In our interpolate function, we need to figure out what sizes to use for loops. These can be gotten from the size function, which returns the size of the array. We also make a copy of our data and call it clean data. Since this variable has the same name as our return variable, it will be automatically returned at the end of the function. Next, we loop through each person. For each person, we loop through each measurement except the first and last. Those need special treatment with linear interpolation, and we leave them to an exercise. Now, for each matrix element, which we index by the variables person and measurement, we check for a very small value. If the value is nearly 0, we reassign it to the average of the left and right values. Note that if those values are also 0, then linear interpolation might still return an erroneous value. In our test for values that are 0, we do not use the most obvious solution, which is to test for values that are equal to 0 using the equals comparison. This is because MATLAB is using floating point numbers, and floating point equality tests can be unreliable. If a number is nearly 0, but for some reason is not stored as precisely 0, then we might mistakenly suppose that it is a normal value. Using a small number that is slightly larger than 0, but still much smaller than our measurement values, is a good way to avoid this problem. In MATLAB, we do not use a return statement. Instead, any returned variables are returned with whatever value they take at their last assignment. Our program contains two loops. One loop is over every person in our file, while the other loops over every measurement for that person. Data parallel programming tries to avoid writing loops over matrices because they are slow and tend to hide the program logic. In this case, we should look for a better solution. A better solution would be to let MATLAB identify all the locations that are 0, so that we only have to loop over locations that definitely need to be replaced. It turns out that MATLAB has a function called find that does exactly the opposite of what we need. It returns all of the non-zero elements of an array. If we ask find for two return values, it will return an array of row values and an array of column values. Each row-column pair gives a non-zero entry in the array. In order to find zeros rather than non-zeros, we first find the result of a comparison with EPS. The result of the comparison is a matrix with ones where data is near 0 and zeros everywhere else. Find returns the indices of elements in our data matrix that are 0. Our new program is even more compact than the last, and we've only looped over those values that definitely need to be replaced. One thing that we have to be careful about is that we only pass find the center of our matrix. The first and last measurements must get special treatment, and again we leave this as an exercise to the reader. Our new function has less loops, but it does not change the theoretical workload of the computer. Some loop somewhere has to go through every value and test whether it is 0, but that loop was written by someone else and embedded in MATLAB's find function. This loop will be faster and less buggy than anything we can write, which means we should take advantage of it. Another question is whether we can do even better with our program. Rather than loop through values of the arrays I and j, we can use the lesson that we learned in the episode on array indexing to interpolate all the missing values in one line. To review, MATLAB provides a complete set of flow control structures including while loops, if-else-if loops, and for loops. It would seem strange that we spent an episode on flow control that ended with a program that didn't have any loops or if statements left. In MATLAB, as in all data parallel languages, loops should be used to control the general flow of the program, but they should probably not be used to iterate through every element of a data structure. It is best to use built-in functions for those tasks. Before you write a MATLAB function, you should ask yourself if there are pre-built functions that you can combine to lighten your programming and debugging load. Before you write a loop or if statement in MATLAB, you should ask yourself if there is a data parallel way to accomplish the same task. In our next episode, we will take a deeper look at more advanced MATLAB function writing, which can make use of the flexible way that MATLAB handles function parameters and returns. Hello, and welcome to another episode of the Software Carpentry Lecture on MATLAB Programming. This is part 2 of the series on flow control. In this episode, we will take a closer look at functions. In the last episode, We introduced the if-else and for loop statements, which provide basic flow control in MATLAB. Another important flow control construct is the function, which helps divide a large program into more manageable sections. Each function represents a single task that can be separated from the whole. We created a function in the last episode to hold our interpolation example. Now we will update that function to be more useful in general situations. Any program can be broken into a series of independent tasks. The task of loading data should be independent from the task of performing a calculation on that data, which should then be independent of displaying the result of the computation. Each subtask has its own set of subtasks. For instance, to load data, one first has to figure out where the data is located, then read it from the disk or network, and finally test that the format is correct. A large calculation often has many subtasks that should be logically independent from the rest of the program. A function can be used to encapsulate each of these tasks into its own logical unit. In MATLAB, most user activity occurs in the main workspace, which can be controlled from the command line in MATLAB's interface. The main workspace has a state, which contains the set of defined variables and their current values. When a user calls a function, she passes some variables to the function as parameters. The function performs its task and may pass some return values to the caller. The function has its own state. It doesn't have access to the variables inside of the main workspace unless they are passed as parameters. As an example, consider the problem of computing eigenvectors. The eigenvectors of a matrix are the set of vectors that only change by a scalar under matrix multiplication. The scalar multiplier is called an eigenvalue, and eigenpairs form a key theoretical concept that is used in many fields. Computing eigenvalues is a subtask that should be handled by a function. MATLAB provides a function eig that computes the eigenvalues of a matrix and returns them in a vector. The same function can compute both eigenvalues and eigenvectors. If we ask for two return values, then the first return value is eigenvectors, and the second is the set of eigenvalues. That means that the first return value's meaning actually changed when we requested two returns. The eigenvalue function, and many other functions in MATLAB, make use of two special functions called inargin and inargout to tell how many parameters were passed into the function and how many return values are expected. Inargout should be thought of as an extra, implicit parameter that is passed to every function. Just like any other parameter, inargout can be used to dictate the behavior of the function. Let's return to the interpolate function that we introduced in part 1 of the flow control lectures. In that episode, we defined a function that would accept time series data that contained bad measurements. All of the bad measurements were assumed to be 0, and our function filled in those zeros by interpolating from nearby values. In this episode, we will make our function more useful by adding extra parameters and return types. First, we will let the user choose a range of acceptable measurements by specifying a lower bound other than the default of 0, as well as by letting them choose an upper bound. We will also add a few status variables to the output. In our new function, we will follow a general MATLAB convention. The first return value should be the result of the calculation, and generally, that value means the same thing no matter how many return values are requested. If the user asks for more return values, those should be treated as status variables. For instance, the min function returns the minimum entry in a vector as its first return value. If another return value is requested, that value holds the index of the location that contained the minimum value. Our new function will accept an optional minimum and maximum acceptable value. It will also declare that it can return up to 3 values. The second return value is the number of locations we replaced. The third return value is the set of indices of locations that we replaced. Note that we are following the pattern of less to more information in our extra return variables. At the start of our function, we test whether a second parameter was passed. If not, then the min is set to the default value of 0. Next, we test whether a third parameter is passed. If so, we find all values that are larger than the max and add them to the list of values to replace. After we've interpolated all of the values that need to change, we assigned the extra return values as needed. If the caller requested a second variable, we assign the length of the replacement vector to numReplaced. If they want all of the locations that were replaced, then we assign the set of row and column indices to the variable replaced locations. To review, functions can be used to encapsulate a single task or idea in a way that separates it logically from the rest of the code, and that separates variable names to avoid accidentally overwriting globally defined variables. MATLAB functions can have a variable number of parameters and return types, and the function has access to the number of each through the use of inargin and inargout. In the next episode, we will examine cell arrays and structures, which are data types that are useful when working with data that is not well suited for an array. Hello, and welcome to another episode of the Software Carpentry Lecture on MATLAB Programming. In this episode, we'll have a look at file input and output. Scientists use a lot of data, and it takes many forms. Almost all of the data that we use can be interpreted as an array, and MATLAB has the tools to convert many common data formats into array structures. In this lecture, we investigate MATLAB's data input and output mechanisms. First, we look at a few functions that open files and translate their file format to a MATLAB data structure. We also investigate functions to print formatted output to the screen. Last, we investigate functions to write arrays and other data structures in common file formats. Importing data can be done in one of two ways. The easiest is to use the graphical interface directly. The graphical interface is easiest for quickly loading a single file, but it isn't really feasible if you have to load a lot of files. The alternative is to call import functions directly. Command line functions can be automated in scripts and functions. Usually, MATLAB can figure out what to do with a file based on its format, but if it is unclear how to interpret your file, you can provide hints to the import functions when you use the command line. The graphical interface has a box that displays the contents of the working directory. One of the files in this folder is named satellite.mat. Files with the .mat extension are MATLAB storage files that store data in a binary format. Since they are designed for use in MATLAB, MAT files can store multiple variables, which makes it easy to save an entire work session in one file. Double-clicking on satellite.mat imports all of the variables into the workspace. In this case, there was only one variable called HRImage. When variables are stored in a .mat file, they keep their original names. Be careful about opening multiple files that contain variables with the same names, as this can overwrite old data. Here is an example of a common file format. Each row of this file contains 3 numbers separated by a space. Text files are not the most efficient way to store data, but they are nice because humans can quickly check what is in the file. There are several commands that handle data from text files, but the most flexible is the command import data. Import data is a wrapper function, which means its job is to figure out what format the file is using and identify the correct function to read the data. Sometimes import data may have trouble identifying the correct format of a file. This is especially true if the file uses an unexpected column delimiter or has multiple header lines. Type help import data to see more information about optional arguments. Wrapper functions help hide internal details from the end user. In this case, import data will call a function like load, xmlread, or imread depending on the file. Users do not have to remember which function to use in every situation. Import data returns the input as a structure. If you haven't done so already, it would be a good idea to look at the Software Carpentry episode on MATLAB data structures, including the episode on cell arrays. When we inspect the elements of the structure, we see that the file's information was broken into a large 3-column matrix called data, a cell array of strings called call headers that are the column headers for each column in our matrix, and a third item called text data that contains a copy of the column headers. If we had more lines of text at the start of our file, these would have been stored in a nested cell array in text data. The structure's format depends on the type of file that is imported. For instance, we can read this spreadsheet using the same import data function. The result is a structure, and each element of the structure is a sheet in the spreadsheet. The other half of file I/O is retrieving results from Matlab. There are multiple ways to save data. We can save a plot or image of our data. We can save printed output, such as a series of commands and their results, or we can export variables to a file. Visualization is a large topic that deserves its own episode. Hello, and welcome to another episode of the Software Carpentry lecture on MATLAB programming. In this episode, we will talk about printing formatted output to the screen and exporting data to a file. Before we start printing to the screen, it is important to figure out what kind of output is appropriate to print to the screen. One common practice is to print intermediate status messages in functions that run for a long time. A good status message can help the user abort a program if it is not performing correctly. Functions that iterate an unknown number of times often have status messages. An example of such a function is the power iteration algorithm, which finds the largest eigenpair of a matrix. It is often used on large, sparse matrices, such as the matrix of weights used by Google's PageRank algorithm. The basic algorithm is embodied in the red equation, which is just a matrix multiplication and division by a scalar. Here is a piece of MATLAB code that computes the power iteration of a matrix A. Note that we loop over the iteration until successive approximations b and b_new differ by at most 1e-5. If we define a large matrix and compute the power iteration, there is no guarantee on how long the algorithm will run. There are several things that can go wrong, including a coding error or floating point error that leads to an infinite loop. One way to monitor the calculation is to compute the stopping criteria and leave off the semicolon. This is not a good idea because it prints 4 lines per iteration. If we need to print several status variables per iteration, the output is both long and hard to read. A better strategy is to utilize the fprintf function, which prints formatted text to a file or to the standard output stream. Clearly, this output is cleaner and shorter than it would be if we had just left off a semicolon. fprintf is mirrored on the printf statement from C or Fortran. The important input is format, which is a string that contains special escape sequences that start with a %sign. Each %sign corresponds to another parameter that will be printed at the specified location. The numbers and digits that follow a % are hints on how to format the number. For instance, %d means to interpret the corresponding value as an integer, and we see that the input I makes sense as an integer. %f means to interpret the value as a floating point number, so the norm is printed in floating point format. There is a long list of formatting symbols that is available at the online help for fprintf. Another important use of printed output is for auditing during data exploration. If you are exploring several kinds of analysis, journaling with the diary function can help keep track of what commands were run and what their output was. MATLAB always tracks the history of commands that were run from the standard prompt. These can be accessed from the history screen or by typing the up key in the prompt. History gets us halfway there. It stores what commands we ran, but it does not store a transcript of the actual output. Using diary, we can find changes to output that might be caused by changes to functions or data files. To turn on the diary, type diary and a file name. If you don't specify a file name, the output is stored in a file called diary. You can turn the diary on and off by typing diary on and diary off. Unfortunately, there is no single function that can store any kind of data. This should make sense because it is important to specify how you want to interpret an array or structure. If you are saving data that will be reloaded by MATLAB, it is probably best to use MAT files that can store your entire workspace. However, keep in mind that MAT files cannot be examined in a text editor, and you are reliant on Matlab or a third-party program to read the files later on. Another option for some data is XML, which is a formatted text file that can store multiple variables. Many times, it is important to export data as a sound or image or other medium. Matlab provides functions to translate arrays or structures into many media formats. Some special video or image formats might require codecs to correctly encode a file, and these can be found at MATLAB's File Central. The important point is that most data can be interpreted as an array. MATLAB can import data in many different formats, and it provides tools to export data structures back into many media and storage formats. In the next episode, we will look at visualization in MATLAB, which includes tools to create plots and images. Hello, and welcome to another episode of the Software Carpentry lecture on MATLAB programming. In this episode, we will examine visualization techniques using the functions plot and imshow. Visualization has always played a big role in understanding our data and ideas. This image from Isaac Newton demonstrates the ideas that led to the integral. In order to clearly express our findings, scientists need to be able to create interesting and relevant images. An advantage that plotting with MATLAB provides is that plots are created directly from the program used to perform calculations. As we will see in this lecture, producing informative plots might require that we transform our data, which is easily done from within MATLAB. MATLAB contains several plotting functions that are highly customizable. The simplest plot function is the function plot, which will create a line graph with one data set for each column of M. In this example, we will use two data sets that contain historical financial data for the Dow Jones Industrial Average and the Standard & Poor's 500. Both files contain 4 columns. The first 3 form a date, and the fourth value is the closing value of one of the two indices on that day. First, we load our data into two variables Dow and SP using the import data function that we introduced in the lecture on file I/O. Then, it is easy to plot the column of closing values for the Dow Jones. The plot looks familiar to anyone familiar with finance, but the axes may not make sense. If you are an economist, you know that there was a market crash in 1987. The crash might be that small bump before the graph starts growing, but it is hard to say. Since we only told MATLAB to plot a vector, the x-axis is the index in the vector. If we pass two vectors to the plot function, it will reassign the x-axis. The first 3 columns in the matrix Dow are the year, month, and day of the associated closing value. We need to transform these into a decimal year. As a rough approximation, we divide the month value by 12 and the day value by 30 times 12. This translates all of the dates into the years unit. This time, when we call plot, we pass the value for the x-axis first and the value for y second. MATLAB chooses the correct values for the x-axis. Generally, MATLAB is very smart about choosing good tick marks for axes and plots. If you want to change them, you can do so in the Tool drop-down menu. If you want to make further edits to the format of the plot, you can access either the Tools or Insert drop-down menus. Most options are available under the Tools menu. The first option, Edit Plot, provides access to all aspects of the plot's format. An easier way to make quick changes is to right-click on the aspect of the plot you want to edit. In this case, we right-clicked on the line plot, which brings up a context menu that has controls for the line style, width, and markers. If you want to make more customized edits, you can do so with the property editor. If you pass 2 inputs to the plot function, we already saw that the first one is treated as an x value and the second is treated as y. In this example, we compare the 2 stock indices by placing them both in a matrix and plotting the matrix against time. Each column of the matrix stocks is plotted as its own curve. The blue line is familiar, and the green line is the S&P 500. Unfortunately, this plot is not too informative because the 2 variables are on different scales. For instance, it is hard to tell which index gained more as a percentage of its starting value. It is best to rescale the sets of indices in relation to their starting value. This will produce a plot of the rate of return of each index. When the values are rescaled, we see that the S&P 500 actually outperforms the Dow Jones, but that it is significantly more volatile. The important point to note is that proper data visualization might take several iterations before the full sense of the message can be found. MATLAB offers several other plotting utilities, including functions to make the standard pie and bar graphs. The hist function can be used to make histograms. If your data requires it, MATLAB can make many kinds of three-dimensional charts as well. Again, all of these plots are fully customizable. Another way to visualize data is to treat a matrix as an image. In this example, we will examine a dataset of public, geolocated Twitter messages near Toronto. We start with the question of from where in Toronto people are most likely to send a geolocated tweet. To answer this question, I recorded all geolocated tweets for 2 months in downtown Toronto. Then I divided the city into a grid and counted the relative number of tweets in each cell of the grid. The result is a data matrix, where each point in the matrix is the relative number of tweets near a grid center on the map. Of course, like many other data sets, this one is best thought of as a matrix. The simplest way to create an image in MATLAB is to call image and pass it a matrix. Unfortunately, this matrix isn't very amenable to imaging. We see a few pixels that are not dark blue, and the rest is just the same color. To understand what happened, we need to take a closer look at the image function. Image takes either an n by m matrix or an n by m by 3 array. If the image is two-dimensional, then each element is treated as an intensity value. If it has 3 dimensions, then each pixel is described by 3 intensity values corresponding to 3 color channels. Image uses a color map, which is an n by 3 matrix to map intensities to colors. For this simple color map, values are taken from the range 0 to 64, split into 4 equal sets, and mapped to the corresponding location in the image. Since the data is not three-dimensional, we only need to use the first column of color map. The intensity values between 0 and 64 are mapped evenly to the rows of the color map, which produces the colored output. There are many color maps in MATLAB which can be accessed by typing help color map. In a moment, we will explore a few of the more standard color maps. An important point about image is that it expects all the values to be between 0 and 64. If the data has a different range, then it is truncated to the range 0 to 64. It is usually better to use image SC, which rescales the values of the matrix to fit in the range 0 to 64, which ensures that the entire color map is used. Unfortunately, we still do not see an image in this data. The reason is that image SC scales data linearly between the highest and lowest points. Our data follows an exponential distribution, which means that the largest values are a great deal larger than the average value. Imaging the logarithm of our data, we see a much more interesting pattern. We can pick out major streets and public areas in this plot. Depending on the data, it might be worth trying other color maps. This color map is grayscale, and lighter values correspond to higher intensities. Color map hot uses a black to yellow heat map. In conclusion, plots and images are powerful tools to explore data, but be sure to take full advantage of the pattern that is in the data. Sometimes you may need to rescale or otherwise edit data to fully capture its meaning. Hello, and welcome to another episode of the Software Carpentry Lecture on MATLAB Programming. In this episode, we will introduce structures and cell arrays, which are two data structures in MATLAB that can be used to store more complex data than the traditional floating point array. In the lectures on arrays, indexing, and linear algebra, we saw that MATLAB's basic data type is an array of double floating point values. A lot of scientific data is reported as numbers, but some data comes in text or other formats. For instance, MATLAB supports strings, which are surrounded by single quotes. It is tempting to try to create an array of strings from the command line, but creating an array of strings just concatenates the strings. Moreover, the second element in the string is the letter T instead of the string 2. In most languages, including Matlab, strings are actually a special type of array that contains characters. Using single quotes to define a string is just a shorthand way of defining the array of characters. Since a string is an array, creating an array from two strings is really just a block matrix operation like we saw in the lecture on MATLAB Basics. Of course, this isn't really what we wanted. And it all comes back to the fact that arrays can contain only simple types like numbers or characters. In order to have a true array of strings, we need an array of arrays. MATLAB has a special kind of array called a cell array that can hold complex types. This means that an array can hold other arrays rather than copying the contents of each array into a larger structure. Cell arrays are one of two related data structures. The other is called a structure. Both can store mixed data types. The difference is in how we index the data. As we will see, cell arrays are indexed by integers, just like regular MATLAB arrays. Structures store data in key-value pairs and can be used as an equivalent to Python's dictionary or Java's hash map. Structures store data in a hierarchy. In this example, we store an array that contains the intensity values of the three primary colors, red, green, and blue, that are required to make one of several different colors. We can see that the array for orange is accessed by the key colors.orange. If you are familiar with dictionaries in another language, this should look familiar. For instance, in Python, we can recreate colors as a dictionary. Each key is a string, and each value is an array with 3 elements. As this example shows, care must be taken when creating key-value pairs dynamically. Here, we assign the key file to the variable a, and we assign s.a to the file name data2_27_11.txt. Instead of creating a field in the structure named file, the file name is assigned to the field a. In order to use the contents of a variable as a key in a structure, we have to surround it with parentheses, which tells MATLAB to use the value of the variable rather than the literal string that we typed in. Using the methods isField, field names, order fields, and rm fields, and using the parenthetic access method, a structure can be used just like a dictionary in MATLAB. However, in a structure, the only legal type of field name is a string. Numbers are not allowed. If you need to use numbers as your storage parameters, MATLAB provides cell arrays, which is our next topic. A cell array is an array that can have one or more dimensions, but unlike normal arrays, each cell can hold a different type of data. The first major change we note is that the cell array is denoted by brackets rather than by the square braces that are used for regular arrays. Also, pay attention to the types of objects that we put in the cell array. Here we have a double, a string, and a boolean. Cell arrays follow the same indexing rules as arrays, but they can be indexed using either parentheses or curly braces. The difference is that using parentheses returns a cell array with a single element, while the curly braces returns the element in the first slot of the array. This might seem confusing, and it is. The truth is, cell arrays were a late addition to MATLAB. The core language was designed with only arrays in mind, so both cell arrays and structures had to be given a few slightly strange syntax patterns in order to maintain full backwards compatibility. If you get an error when you are working with cell arrays or structures, be sure to check the output of the function isCell or isStruct. If the answer is 1, then the data type was a cell array with one element. If the answer is 0, then the data type is the type of whatever was stored in that location. This analogy might help you tell the difference. If a cell array is a series of mailboxes, then accessing a cell array using parentheses is equivalent to identifying a single mailbox. Indexing the cell array using braces is like getting the contents of the mailbox. There are several functions that will help you navigate between cell arrays, structs, and strings. isCell and isStruct are pretty obvious. The function char will flatten a cell array of strings into a regular array of characters. Earlier, we noted that an array of characters is just a string. Cell arrays can have more than one dimension, just like regular arrays. Indexing shortcuts appear to work as expected, but note the slight difference in the output. Also, if we assign a set of cell array contents to a variable, we only get the first variable in the index. This is MATLAB's best guess as to what we want, because we are asking MATLAB to assign the value in each cell to the variable call. In reality, this request doesn't even make sense. If we really meant to get a column of cells, then we need to use cell indexing instead of content indexing. To review, we'll compare structs and cell arrays to Python, another common programming language. Python and many other languages have dictionary data types that hold data in key-value pairs. A struct acts like a limited dictionary, but the limitation is that it only accepts strings as keys. A cell array is not a dictionary at all. It is more like a list in Python because it can hold mixed data types, but it is accessed using numerical indices. The important thing to remember is that cell arrays and structures are both designed to hold data with heterogeneous types. Thanks for listening.